Hello all. So welcome to this new lecture in this course on time series forecasting with applications in R. So until last week what we studied was we stopped at ARIMA process. If you remember the last session towards the end we took up, and then in particular we looked at this ARIMA PDQ process that you see on the slides in front of you. So what we'll do is we'll again pick it up from here. So we'll expand more on non-stationary time series per se, because if you remember in the last lecture we discussed that almost 90% of the examples are non-stationary, right? I mean you should expect some trend, or there should be some seasonality, right? Or there should be some pattern within the time series which makes the series to be non-stationary. So elaborating and then kind of expanding the non-stationarity aspect of a time series is more important than expanding the stationary time series. Okay. So if you remember the definition of an ARIMA PDQ process, this is more like a quick revision, is in the first place is a non-stationary time series process. So let's say if you have a non-stationary process YT which follows ARIMA PDQ. So when do you say that YT follows ARIMA PDQ? Let's say if you difference this YT d times, right? So if you difference this time series process d times, and if the resultant series or if the output series is a stationary ARMA PQ process, then we can actually say that the initial time series YT happens to be ARIMA PDQ. Okay. And then again, as discussed in the last session, the first couple of orders, so let's say P and Q, stand for the autoregressive and the moving average orders of the process, while the number of times you may want to difference the series is given by D. Okay. And then if you remember, we took up a simple example. So let's say if you start with a particular process, let's say YT, right? And then let's say if you apply the differencing operator twice, okay. So nabla operated 2 times, and let's say if you assume that the resultant series is WT, which follows a ARMA 2-1 process, and then obviously the assumption is that this ARMA 2-1 process would be stationary. Okay. Then we can say that the initial time series YT happens to follow a ARIMA 2,2,1 process. All right. Now again, why 2? The first 2 and the last 1, because they correspond to the AR orders and the MA orders of the stationary ARMA process. And then since you have differenced the series 2 times or twice, the middle value of D happens to be 2. Okay. Now just as a quick revision, we will kind of revise the different kinds of differencing that we studied in the last lecture. Okay. So the first one is lag 1 difference. So lag 1 difference, all of you know that the operator is nabla. So if you apply this nabla operator on YT, it kind of gives you YT minus YT minus 1. So you basically take the current value of the time series and then subtract one past value. Alright, so YT minus 1. And then in general, we can actually extend this to multiple or future lag. So let's say lag 2 difference or lag 3 difference. So in general, if you have a lag D difference, so differencing at a lag D is nothing but 1 minus b to the power d, right, applied on YT. Okay. So 1 minus b to the power d applied on YT. So by the way, if you remember, when is this lag d difference kind of used is when there is seasonality, right. So if you want to difference directly at a particular lag, so if you look at the formula here, formula is YT minus YT minus d, right. So the lag between the subscripts here is nothing but d. So we call this as a lag D difference, right. And then the other kind of a differencing is Dth difference. So let's say if you have a strong trend which is not linear, but let's say quadratic, or has some higher power, let's say cubic, right, and so on and so forth, then there might be a requirement of differencing it those many times, right. So in the last lecture we took up an example where if you have a quadratic trend, then the amount of differencing which is required is twice, right, and then after you difference twice, then we can actually get a stationary model. So to be able to control the amount of trend we have, we require to difference the series those many times. So let's say in general, if you want to apply the dth difference, and then formula is nabla raised to the power d, which is nothing but 1 minus b raised to the power d applied on YT. Right. By the way, in all these formulas, this capital B is nothing but the backshift operator. Okay. And then couple of remarks or couple of points here, that if the trend MT is a polynomial function of order D, then the dth difference applied on YT would be stationary. while if the data is seasonal with, let's say, some period d. So period d means what? So if you have a monthly data, then period is 12. If you have a quarterly data, then period is 4, and so on and so forth, right? So if the data is seasonal with a certain period d, then a particular lag d difference is applied, and then that would kind of remove the seasonality aspect from the series. Okay. So I think this slide sort of sums up all kinds of differences that one can apply depending on if you have a trend or if you have some seasonality behavior in the series, and so on and so forth. Okay. And then the last slide in this lecture here would be kind of a simulation again. So what we have in front of us is a simulated sequence of an ARIMA 1,1,1 process. Okay. Now by the way, all these things have been done in R, right? So all the simulations and all the calculations have been done in R. Right? So a particular ARIMA 1,1,1 process where the coefficients are nothing but 0.7 and 0.2. So 0.7 corresponds to the AR coefficient, which is phi 1, and then 0.2 corresponds to the MA coefficient, which is theta 1. Right? And then this is just a simulated series or simulated sequence of that particular ARIMA model. And then clearly you can see that this series is not stationary firstly, right? Because you have like local trends. For example, you have a trend here and then possibly a trend here, right? But what it could mean is that since both these coefficients are less than 1, right? So if you difference this series once, right? If you difference this series once, then possibly we can get hold of a stationary ARMA process with orders 1, 1. Right? And again, why stationary? Because again, like I said, if you remember, the criteria of a particular ARMA process being stationary is that if both these coefficients happen to be between -1 and 1, right, then we can actually say that the ARMA process is stationary. Okay? So even though this initial ARIMA 1,1,1 process is non-stationary, of course, but then differencing this once would produce a stationary ARMA 1,1 process. Right? So this is a broad idea about ARIMA processes, and then what would happen if you difference such ARIMA processes, and then at the end of the day, if you difference an ARIMA process, we kind of get a stationary ARMA process with the corresponding orders. Right? So now probably in the next slides or in the next set of slides, we'll kind of expand more on non-stationary aspects, then how do you deal with, let's say, seasonality, right? And then we'll talk about a few tests of stationarity. So can you somehow perform some hypothesis testing to kind of prove or kind of show whether a time series is stationary or not, all right? And then again, we'll kind of again expand on different types of seasonality. And then towards the end, we'll focus on one particular seasonal model, which is SARIMA, okay? So SARIMA is a natural extension of ARIMA. So we'll talk about how do you bring in the idea of seasonality along with the trend. Alright, so we'll now discuss a few aspects about seasonality and its features. Alright, so what exactly do you mean by seasonality? And then if you remember one prior lecture that we had, we kind of expanded on different kinds of non-stationary behaviors, right? And there we talked about trend, we talked about seasonality, we talked about irregular component, we talked about changing variance, right? So in the next few minutes, we'll specify more about a few aspects about seasonality. So initially we'll again give a few more examples. So just to acquaint all of you with the idea of what do you mean by seasonality and what are the few examples where seasonal behaviors or seasonal structures can be seen. Okay? So firstly, seasonality is a regular periodic variation where the period of cycle is generally less than 1 year. Right? So again, if you think about temperature data or rainfall data, so what one can observe is, so in summer months, as we discussed even earlier, so we kind of typically see hotter summer months, right? So temperatures are at their peaks, right? And the same behavior kind of repeats itself year by year, right? So the period of repetition or the period between one of the peaks and the next peak is usually less than or equal to 1 year, right? And then such seasonal patterns are usually predictable, because what would happen is that if you want to kind of jot down seasonality using a graph, then seasonality would be something like you have a repetitive pattern, something like that, where the peaks correspond to some typical months over the year or something like that, whereas all the troughs correspond to some other months probably. But then such patterns are kind of predictable, right? Because when such a series is kind of coming down and the series is at its trough or at the bottom, then one can actually expect that it should probably rise back again from here, something like that, right. So, such seasonal patterns are usually predictable, and then factors behaving similarly at a particular time of the year or month or week are called as seasonal factors or seasonal patterns, right. So, there should be some repetitive behavior at a particular month of the year or at a particular day of the month or at a particular week of the month, right. So, all these ideas kind of amount to seasonality. Okay. And then in general, seasonality is kind of caused by, let's say, cycles of seasons or let's say different holidays. So, in India especially, let's say if you have higher sales during Diwali, Dussehra and then Holi, etc. So, all these kind of depend on holidays, right, or regular changes in behavior or let's say biological rhythms and physiology in response to periodic changes in the environment. So, all these are kind of causes of seasonality, right. So, if you want to summarize this paragraph, you can write down causes of seasonality. So, seasonality can be caused due to different reasons, let's say cycles of seasons, then different holidays, or let's say regular changes in behavior, etc. and so on. Now, I think this slide again gives you several more examples of seasonal behavior. So, let's say animal migration. So, in a particular time of a year, so there might be larger amount of animal migration as compared to let's say some other months, okay, or let's say increase in sales of coffee or warm clothes during winter, right, or let's say increase in sales of fans or ACs during winter, right, etc. So, let's say so it all depends on when the sales are happening and when the sales are kind of increased or decreased. Yeah, by the way, this should be summer. So, let's say increased sales of fans or ACs during summer. So, again it all boils down to different seasons within a year, okay, or let's say clothes and firecrackers sales during Diwali. So, again due to let's say holidays. So, this reason could be due to holidays or again amounting to seasons, right. Then the next one could be let's say increased unemployment in June. So, what happens typically in June is that since most of the graduates are kind of in the job market, then probably one might see slightly more unemployment as compared to some other months, where possibly all the graduates have been placed and probably they have started working in some industry or some academia and so on and so forth. But typically when the college session ends, so let's say typically in April, May or by mid-June, then starting from June onwards, one can actually observe slightly increased rates of unemployment. Okay. Or the last one could be something like increase in viral fever cases during change of seasons. Right. So, again all these are kind of revision sort of examples where one can actually experience some seasonality. Okay. Now, why exactly is it important to study seasonality in the first place? Right. So, reasons to study seasonality. Now, of course, there could be many more reasons, but then these are typically some of the important ones. So, the first one could be something like better planning for a temporary increase or decrease in let's say labor requirements or inventory or training or periodic maintenance or let's say supply chain management, etc. Right. So, I think the key here is better planning. So, better planning in terms of multifold different areas. So, let's say inventory management, supply chain management, operations, maintenance, etc. And then once you identify a seasonal pattern or a seasonal repetition, eliminating it from the time series for studying some other components, let's say trend or cyclicality or the irregular component becomes all the more important, right. So, reasons to study seasonality is kind of eliminate that, right, because at the end of the day seasonality amounts to non-stationarity. So, all of us have seen that. So, if a series is non-stationary, one has to kind of identify that and then try to remove that. Okay. And then there could be one more reason which is kind of interesting is in regards to forecasting. So, let's say forecasting future seasonal patterns such as let's say climate changes, right. So, there is a term called as climate normal. So, what do you mean by climate normal is climate normal is nothing but the 30-year average of a weather variable for a given time of year. Right. So, climate normal means on an average what should happen over a 30-year time span. Okay. So forecasting future seasonal patterns, let's say climate changes, or let's say future temperatures, future rainfall. So all these are kind of areas of interest. Alright, so now the next thing we'll study some typical graphs or graphical techniques to kind of detect seasonality, right? And I think all these graphs would be kind of easy to digest and understand, and then they'll kind of present a much more clearer picture as to how do you visualize seasonality in multiple examples. Okay? Now possibly all these could be plotted and then their combinations henceforth, but then these are typical plots that one can actually draw. So the first one is, let's say, simple time series plot or run sequence plot. So by the way, this is nothing but the usual scatter plot that we all kind of plot as a very first idea. Or what one can do is one can have a seasonal plot or a seasonal sub-series plot, or the next one could be something like multiple box plot. So corresponding to each month of a year, we can actually plot a single box plot for that month, right? Or one can actually plot some ACF plots or spectral plots and so on and so forth. So we'll try to elaborate on a few of these plots, and then we'll bring in some examples and then kind of show you that how to draw these plots and how to visualize these plots. Okay. Alright, so now the first one is a simple time series plot, or it's also called as a run sequence plot. So run sequence plot is nothing but a scatter plot of the time series data. The only difference is the x-axis is typically numbered as per the time frame. So, by the way, the example here is average daily gas flows data. Alright, so the amount of gas which flows from, let's say, the manufacturer to a consumer through pipelines and so on, and then average how much gas flows on a daily basis. Right? And then this is a run sequence plot. So run sequence plot means nothing but you're basically plotting the data in a sequence as per the time frame, and then each entry gives you a run basically. And then this is also called as a typical or simple time series plot. So on the x-axis, if you observe, we have all the months, right? So let's say July of 2008, then April of 2009, then January of 2010, then October of 2010. Right, then July of 2011 and so on and so forth. So I think this data is more like quarterly data, right? So if you observe a pattern here, the data is more like a quarterly data. So let's say July, then April of next year, then January, October, July. Obviously, you have few months which are not being listed on the axis, but then still you have the data for that. But the data is quarterly data, right? And then here, if you simply observe the plot, you can clearly see a quarterly seasonality, right? So you see typical peaks and then typical troughs, right? Repeating themselves after every fixed quarters, okay? So this is a very typical kind of a simple time series plot or run sequence plot. So just by observing such a plot, one can actually make out the extent of seasonality, right? So one can actually make out the extent of seasonality and the typical behavior or typical time span or the period of seasonality. And then by the way, this horizontal line that you see here, which is the blue line, gives you the mean. So let's say if you want to indicate as to what is the average daily gas flows data and then average of that average, right? Something like that. So typically here, the average of the average is close to 500. So a few more points on the prior plot, which is the run sequence plot, as to where exactly can you make use of such a plot, or the plot helps in identifying what exactly, right? So one can actually identify all these patterns. So seasonality present in the series, of course, right? And one can actually identify any shifts in location of the seasonal patterns. So again, if you go back for a second, so for example, this horizontal line is nothing but the location or the mean, right? So if you observe in any aspects of this graph, if the gas flow value is kind of deviating towards one side of this horizontal line, then one can actually expect some shift in the location, right? But here obviously you can't make it out because there is no shift in the location. But then if there was, then what would have been observed is that you would have observed some local behaviors where the values are kind of drifting away from that horizontal line, okay? So one can actually observe some shifts in the location, or one can actually observe some shifts in the variation. So shifts in the location and shifts in the variation also. So how exactly? So shifts in the variation could mean something like, so again I'll try to replicate the same plot. So let's say this is the horizontal blue line which indicates the mean, and then let's say initially the average gas flow is kind of behaving like that, but then towards the end the average gas flow is kind of behaving like that. Okay. So even though you have a seasonal behavior clearly, but then the variation is not equal, right? So you have a fanning out kind of a pattern. So initially the average amount of gas flow is kind of restricted in a tighter range, but then as you go down the quarters or down the years, if the average gas flow is kind of increasing in that manner, then one can actually expect that the variance also is kind of being affected. Okay. So such a plot is kind of really important in identifying all these ideas. And the last one is one can actually identify the presence of any outliers. Okay. Alright, so now the next plot is again a simpler one, it's called a seasonal plot. Okay. So what exactly do you mean by a seasonal plot, and then how do you draw a seasonal plot? So the time series is plotted against the individual seasons in which the data was observed. Okay. And then one advantage of the seasonal plot is that the underlying seasonal pattern can be visualized more clearly. And then the third advantage is that it sort of identifies years when the pattern changes. Okay. So let's say if you have a temperature data, and if you want to kind of identify in which year the temperatures were slightly higher than all the other years, or in which years did you observe harsher winters or harsher summers, right? So all these reasoning based questions can be answered using a seasonal plot on a visual manner. Okay. So we'll see an example of a seasonal plot. So again we are using the same data as before, which is the average daily gas flows data, and then this is a very typical seasonal plot. All right. Now what exactly is happening here? So on the x axis, if you observe, we have all the months in a particular year. So let's say January, February, March, all the way up to December. Okay. So this would be our typical year, and then in the graph itself you see different colors. So black, orange, grey, and then blue. So each color kind of corresponds to one season or one particular year. All right. So let's say what happened in, let's say 2020 might be given by the black line. Then what happened in, let's say 2021 might be given by a different color, let's say orange. Then what happened in 2022 would be given by, let's say, a silver color, and then what happened possibly in 2023 might be given by the blue color. All right. So on the x axis you have within year, so each month being plotted, and then the graph itself kind of gives you the behavior across years. So one particular curve or one particular color kind of signifies one particular year. So in this case one can actually compare between years, right? So let's say if you talk about August, right? So during the August month in, let's say 2022, which is the blue line, okay, or 2023, which is the blue line, as compared to, let's say 2020, which is the black line. So can you see a difference here? So let's say the black line is way above the blue line at this point, at the August point, right? So what do you mean by that? So you had, on an average, the daily gas flow was much more larger in the year 2020 as compared to 2023 or 2022 and so on. Okay. So one can actually compare in a particular month what changes one can observe across years of the same data. Right. So this is a typical seasonal plot. So what we do is we have a particular year plotted on the x axis and then values corresponding to different years in the graph itself. Right. Now we'll kind of shift to a slightly different data. So the next data is the airline passengers data, and then probably you must have seen this data even earlier. So what we have here is that, so firstly this data is inbuilt in R, all right, and then this kind of gives you the number of airline passengers who are kind of traveling in thousands over all these years. So 1949 all the way up to 1960, and then of course you have all the months. So this data is a monthly data firstly, right, and again without even plotting anything, just by looking at the structure of the data and the name of the data, one can actually assume that there has to be some seasonality involved, right, because the number of people who travel in airlines might be slightly more in summers than in winters, right? Because in summers one has a few more holidays as compared to winters, and so on and so forth, right? So what we have here is we have monthly data from January, February, all the way up to December, and then over all the years, right? So let's say all these are the individual values. So 112, 115, 145, 171, etc. Okay. So using this data, we'll create a few more plots. So the next one is called a seasonal plot of the data set. So again, I think this is the exact same plot that we had earlier, right? And probably this would be slightly more clearer than the first one, than the earlier one, because what we have here is we are kind of, again on the x-axis we have all the months, so January, February up to December, and then we are essentially plotting the number of airline passengers within that year on an yearly basis. So each color kind of represents one year. So 1949, 1950, 1951, 52, all the way up to 1960. All right, and then for each year you have a different curve, right? So again the same story. So let's say if you go back to the month of, let's say, July or August, right? So one can actually see a drastic difference between the top curve and the bottom curve, right? So whichever years they are. So I think the bottom curve corresponds to 1960, the top curve corresponds to 1949, all right, or exactly the opposite. Exactly the opposite, my bad. So the top curve corresponds to 1960, while the bottom curve corresponds to 1949. And one can see huge differences in the number of passengers who travelled in airlines between 1949 and 1960 in the same month. So let's say July or August, or for that matter any other month. Okay. So in that sense, a seasonal plot kind of gives you a lot of information, not just for a particular season and a particular year, but across all the years as a comparison. Now the next one is called as a seasonal sub-series plot. So what do you mean by that? So such a graph kind of makes the evolution over a time clearer. So what do you mean by that? So we have a graph, and then inside the graph we have some blue lines, right? So those blue lines kind of represent the means of the individual groups or the averages of the individual groups. So one can actually see the averages clearly. So one can actually figure out as to where exactly the averages are lying also. However, this plot has a disadvantage that between season analysis is difficult. For example, one can't compare the number of passengers between 2 months. So let's say if you want to compare between July and August or between July and December. So it's slightly hard to kind of compare such a thing. Okay? But we'll take up one example of this. So this is a very typical seasonal sub-series plot. So now what is happening here is, again on the x-axis you have all the months, and then typically let's say if you take any particular month, right? So let's say January. So this is more like the extent of the number of airline passengers in January over all the years. So 1949 to 1960. So the minimum is this much, this is the maximum, and then the blue line sort of represents the average. Okay. So in January over all the years from 1949 to 1960, what is the behavior in the airline passengers? Right. So if you see, for example, July or August, right? So again the same thing. So in July over all the years from 1949 to 1960, the extent of the number of passengers is roughly from 100. So let's say this is 100, right, to something like 600. So one can actually get a range of the particular observation one is trying to estimate in a particular month over all the years along with the average which is plotted. Okay, so probably in the next session what we'll cover is we'll try to extend this idea about seasonality, and then like we discussed earlier, we'll try to merge all these ideas into how do you kind of define a particular model of seasonality which is called as SARIMA. Okay, thank you.